Welcome to the second lecture for Chemistry 418, Nuclear Chemistry. This lecture is on nuclear properties. The lecture on nuclear properties covers a broad topic range. The readings for this lecture can be found in Chapter 2 of Modern Nuclear Chemistry and Chapter 1 in Nuclear and Radiochemistry, the Introduction, and Chapter 2 in Nuclear and Radiochemistry on atomic nuclei. The lecture is going to cover some interesting concepts and ideas related to nuclei that are used to understand some very fundamental properties that are the basis of what we'll explore later in the course. These include that the number of nucleons, the neutrons and protons, have an influence on the nuclear properties. We're going to see that nuclei with odd numbers of protons and odd numbers of neutrons are inherently unstable. In fact, there are only 4 stable isotopes that have an odd number of neutrons and an odd number of protons. We're going to see that trends in masses of the nuclei are going to be used to determine information about their properties. And then we're going to explore a term called binding energy, which is the difference in the total nucleon mass and the mass of a specific nucleus. For example, you look at the helium nucleus. It has 2 neutrons, 2 protons. One would think that the mass of the helium nucleus is just the sum of 2 neutrons and 2 protons. We're going to see that that is not the case, and the implications for that difference on the nuclear properties are going to be discussed. We're also going to explore how binding energy, this difference between the mass of the total nucleons and the mass of the specific nucleus, is going to be used to explain fission, fusion, and abundance of elements near iron. We're also going to talk about reaction energetics, the energy from nuclear reactions, and we're going to apply E equals mc squared. All we're looking at is changing of mass, and that goes into energy, or if we change energy into mass. So the energetics of nuclear reactions are actually an application of E equals mc squared. We're going to talk about nuclear stability from mass change, and we are also going to introduce the concept that nuclei have shape. Here's an example of a spherical nucleus, and I would think that most people would believe that that is the general shape of a nucleus, and for the most part, most nuclei are spherical. However, we're going to introduce the concept that nuclei are actually not spherical. What does that mean? And the implications for nuclear properties, nuclear stabilities, and radioactive decay are going to stem from some differences in the nuclear shape. And we'll use this baseline information throughout the course. Then we're going to end the discussion on nuclear properties, talking about nuclear quantum properties, primarily spin, parity, and magnetic moment. I'm sure you've probably overlapped and seen some of these terms already, so it's going to be a brief review talking about how these properties are derived from the nucleus and the properties of the nucleons within the nucleus. Nuclear properties are basically derived from systematic evaluation of measured data. So, for instance, masses, how nuclear masses change. Imagine that you have an isotope and you keep adding a neutron to it. So the element is the same, the neutron number changes. Well, how does that mass change systematically by adding a neutron? One would think that every time I add a neutron, the mass increase would be based just upon that neutron addition. But it's actually a little bit different than that, and it has to do with the fact that the mass of the nucleus, some of that mass can be converted into energy that helps keep the nucleus together. So we'll look at masses and how those change systematically. And then we'll talk about distribution of matter, and what that really means is density within the nucleus. We'll discuss those terms and how they're derived. So fundamentally, size, shape, mass, and stability of nuclei follow patterns that can be understood. And once you have these patterns and you understand them, one develops models so that these trends can be described. So you interpret that data. That's a classic method that's been used in nuclear physics, and we'll describe how that pattern is used not only for these fundamental nuclear properties, but in methods where one evaluates decay of nuclei, trying to understand how decay occurs. So an average size and stability of a nucleus can be described by an average nucleon binding in a macroscopic model. So there will be a macroscopic model. The first models we'll talk about were very basic. We will talk about a liquid drop model. And then detailed energy levels and decay properties can be evaluated with quantum mechanics or a microscopic model. So we're going to describe how we go from a macroscopic model to a microscopic model. And an important example of trends in the nuclei can be observed just by looking at stable nuclei and the number of neutrons and protons that are in those stable nuclei. The number of stable nuclei is known. One can evaluate the number of neutrons and the number of protons for a given stable nucleus and just do a simple characterization. Say, okay, let's divide the number of stable nuclei based upon if they have an even number of neutrons and an even number of protons. And as we see here, there's this trend where there's 160 stable nuclei, so stable isotopes, that have an even number of neutrons and even number of protons. There's about an equal number that have odd number of neutrons, even number of protons, and then an odd number of protons, even number of neutrons. There are only 4 stable nuclei that have odd numbers. So odd number of neutrons, odd number of protons. Chances are, if you have a isotope that has an odd number of neutrons, odd number of protons, it's not going to be stable. So this very simple property, the very first attempt at understanding some nuclear physics, count the number of neutrons, count the number of protons. So the number of protons and the neutrons are important in the nucleus. And again, if we look at any given element, there are ranges where you have a stable configuration. And if I start adding too many neutrons or taking too many neutrons away, that isotope is no longer stable. Let's start by looking at what are the 4 stable odd nuclei. They happen to be some of the lighter stable nuclei. And if we look at the proton number of the stablest elements, well, 1, 3, 5, 7. So hydrogen, lithium, boron, nitrogen. Chances are we're going to look at those elements and they're going to have a stable isotope with an odd number of neutrons and protons. So hydrogen, 1 proton, 1 neutron. Hydrogen 2, deuterium, it's stable, low percentage. If we go to lithium, we see that lithium 6, as shown here. 3 protons, 3 neutrons, stable. Boron 10, 5 protons, 5 neutrons. And then nitrogen 14. The next odd numbered Z, so odd number of protons for an element, is fluorine. And if you look at fluorine, there is no stable isotope of fluorine with an odd number of neutrons. So these 4 isotopes here are the only 4 stable isotopes that have an odd number of neutrons and an odd number of protons. From the first introduction of this lecture, we said that mass is going to be an important consideration in determining nuclear properties. So look at it this way. We can evaluate the mass of a given isotope. And what's the difference between the actual mass of a nucleus and the expected mass from the atomic number? So, for instance, if we define carbon-12 as 12 AMU, that's the definition, we can talk about something called a mass excess. If the mass excess is negative, then the isotope has more binding energy than carbon-12. And the mass excess, it's a term that we're going to introduce. It's this delta term, and it's equal to the nuclear mass minus A, the mass number. So we can get a value, this unit's in MeV, so we take a mass unit and we're converting it into MeV, which is an energy unit, so mega electron volt. So we're going to talk about this mass excess in terms of MeV. And the reason we're doing that is the numbers were 1, easier to handle, but 2, they're useful for determining energetics, since we're just taking the change in masses and already converting that to energy. And how do we do that? Well, we use E equals mc squared. So this is what's interesting, or a nice aspect of this work with radioactive decay, we get a relationship between energy and mass, and it's the Einstein equation. As an example of what we mean by mass excess, if we look at sodium-24, the AMU, the atomic mass, is listed here. It's just a little bit under 24, right? So 23.9909, etc., minus 24 is equal to this very small negative number. And I already gave you this value that we're going to convert it from atomic mass units into energy. And it turns out that one atomic mass unit is equal to 931.5 MeV. So about one atomic mass unit is about 1,000 MeV, kind of a reasonable rule of thumb. So if I take this value, multiply it by 931.5 MeV per atomic mass unit, I get that the mass excess for sodium-24 is equal to negative 8.418, etc., MeV, mega electron volts. So this is a value that we could use for equations, and it's a way of quantifying how changes in this atomic mass unit can be used to help us understand reactions. So right now all we've done is defined this mass excess term, which is the atomic mass unit minus the A of that isotope. We get a value, we multiply it by 931.5, and we get this mass excess. You won't have to do this. There's actually large tables with this mass excess data. Remember, it's the delta. The table of the isotopes, for instance, what we talked about in lecture 1, has all the mass excess for all the isotopes listed. And this is all derived from E equals mc squared. In the previous slide, we focused on nuclear masses, but since we're talking about atoms, we really need to consider the atomic mass, and let's convince ourselves that basically the electron mass doesn't matter in the atom. So we can talk about the nuclear mass as found from the atomic mass. So the nuclear mass is equal to the atomic mass minus the mass of the electrons plus the binding energy of those electrons. Now the electron rest mass is about half an MeV. We know that atomic mass unit is about 1,000 MeV, so the 0.511 MeV electron mass divided by 931.5 MeV is a pretty small number, 5.5 times 10 to the negative 4 atomic mass units. So the fraction of the mass that the electron has compared to a one nucleon is pretty small. So in that regards, eliminating the electron mass from this equation makes sense. The total binding energy of all electrons can be given as this equation, where the binding energy is equal to 15 z to the 7/3, where z is the number of protons in eV. As an example, with uranium, a z of 92, the binding energy is half an MeV for the electrons in uranium. So a small number. These masses are in MeV. Again, this number is also pretty insignificant. So both the binding energy term and the electron mass term can be neglected. So that allows us just to focus on the nuclear masses in any decay from parent to progeny. So our concept with using the nuclear masses is relevant. We can look at the beta decay and determine the Q value for this route. Using the mass excesses, beta decay, we have an isotope that converts an excess neutron to a proton, gives off an electron, an antineutrino, and some energy. So let's consider the beta particle, the electron, to be part of this charged new atom that's made. Since we're converting a neutron into a proton, Z goes to Z plus 1, the charge goes up. Well, let's just consider this electron as part of this. Okay, we're neglecting the binding energy, but that's okay. We know that that's not something that we really need to be concerned about. So the Q value is equal to the mass excess of the parent minus the mass excess of the progeny. An example of this, calculate the Q value for the beta decay of carbon-14. Carbon-14 decays to nitrogen-14, and beta particle plus an antineutrino plus Q. Rearrange the equation, solve for Q. So Q is equal to the carbon-14 mass excess minus the nitrogen-14 mass excess. We can look up mass excess values from this site, and we plug in those mass excess values, and we get 3.0198 minus 2.8634 is equal to 0.156 MeV. These values are in MeV. So now we have a route for calculating energies for decays. And we've shown that we can calculate the Q value for the beta decay of carbon-14. On the previous slide, we saw that the Q value for the decay of carbon-14 is 0.156 MeV. I also told you that you could get the mass excess data for the isotopes involved, so carbon-14, nitrogen-14, from the nuclear wallet cards, and the website for the nuclear wallet cards listed here. So I'll show you what that would look like if you were to go to this website and click on it. You would find a periodic table that would pull up, find carbon and nitrogen as they are shown here. Click on them in series. So you would select carbon, get the data, select nitrogen, then get your data. And what this would look like is shown here. This is Z of 6, so that's carbon. The data, mass excess in MeV, value shown here. The nitrogen data, Z of 7, nitrogen 14, shown here. So again, the Q value would be the parent 3.01989 minus the daughter 2.86341. And that's how one can calculate the Q value for that specific reaction. Using the same methodology, one can evaluate the Q value for positron decay. And again, for the positron decay, it's neutron deficient. So proton is converted into a neutron. So you have an isotope that decays. It goes from an isotope with a given Z to an isotope with a Z minus 1. A positron comes out, which is basically an antimatter electron, a neutrino, and then the Q value. So let's consider the Q value. Now, fundamentally, we have two extra electrons to consider. I have this atom that decays. I've taken a proton and converted it to a neutron. So this atom has an excess electron. This positron that comes out, we'll also treat that as an electron. So we have two extra electrons to consider. Positron and an additional electron from the daughter. The mass of each electron is 0.511 MeV. So we need to add this, we need to consider this term, 1.022 MeV total from the electrons. So we look at a Q value is equal to the parent mass minus the sum of the progeny mass and 1.022 MeV, the 1.022 MeV accounting for the electron and positron. Let's consider the positron decay of niobium-90 to zirconium-90. A positron is emitted. We look up the mass excesses for niobium-90, zirconium-90. The positron and electron mass is listed here as 1.022 MeV. And we get this value of 5.089 MeV. We can do the same calculation for electron capture. In this case, the electron comes from the parent orbital. Parent can be designated as a cation to represent this behavior. So we have a parent here that takes an electron, then a proton is converted into a neutron. A neutrino is emitted. So from this, the Q value is just equal to, well, this gets neutralized, so we don't have to worry about electron mass. So it's just the mass of the parent minus the progeny mass. So let's look at the electron capture of bismuth-207 to lead-207. Again, that's moving down the periodic table. We can negate and ignore the neutrino. The Q value is listed here, so we just need to get the mass excess for these isotopes. We obtain the mass excess for these isotopes. We run the equation, and we get that electron capture of bismuth 207 is 2.3947 MeV. We can do the Q value calculation for alpha decay, and this is shown here, where I have an isotope, it decays, it emits a helium nucleus, which is shown here. The progeny loses 2 neutrons, 2 protons, so the A is reduced by 4. The proton number is reduced by 2. So let's consider the alpha decay of americium-241. It decays to neptunium-237 and the alpha particle. So the Q value is equal to the mass of the parent minus the sum of the progeny mass and the alpha particle mass. So we can use mass excess to determine this. We can also do this with something called the Q value calculator, and I'll show you how to use that later in this lecture. But let's consider the terms that we have here. One needs to get the mass excess of americium-241, neptunium-237, and helium-4, the alpha particle. The mass excess of americium-241 is provided here. The mass excess of neptunium-237 is listed here. And the mass excess for the helium-4 nucleus, which is the alpha particle, is listed here. And I pulled this out of compendium of information and data that's in the back of the textbook, Nuclear and Radiochemistry. So we get this Q value. And then if I look at the alpha decay energies for americium-241, I actually find that the Q values are over the alpha decay energies. And that's to be expected because the Q value is the total reaction. When we discuss alpha decay, we'll go into this in a little bit more detail. But the Q value is the alpha decay energy plus the progeny recoil. Therefore, the actual alpha decay energies will be close to the Q value, but slightly under that value. We will calculate the relationship later this lecture. Now we showed the Q value for specific reactions. Actually, you can determine the Q value of any reaction. So just treat the Q, the energy, as part of the equation and solve for Q. So example, imagine this reaction where we take some iron and we have a target of iron and we hit it with helium-4 and cobalt-59 is made along with a proton. What's the energetics of that reaction? Well, we can write the Q value. It's the mass of the products minus the mass of the reactants. We have the mass, C squared, makes it into energy. The Q value calculator, which we'll talk about, I can enter this information and out comes a value. I can get the mass excess and Q value data that are necessary from a number of different sources. This table of the isotopes, Q value calculator, and then atomic masses of isotopes. This Q value calculator is a tool from the National Nuclear Data Center at Brookhaven National Laboratory that you can input the reaction information and the Q value will come out. Q values can also be calculated using websites. One does a search for Q value calculator. 2 sites will show up. One will be from Brookhaven National Laboratory, another from Russia. Let's look at both these, but focus in on the one from Brookhaven National Laboratory. So this Q value calculator, the data that it uses, the mass evaluation data is shown here. So in our previous slides, we went over how to do the calculations from the mass excesses. This website uses the mass excesses found here. And you can read some of the disclaimers on this site. And for instance, NN or N, lowercase or uppercase NN is listed as a neutron. So there's a few things this site can do. First, we'll start with the summary. And if we just put in an isotope, let's start with bismuth-212, and say submit, it'll give me all the information about the decays of bismuth-212 and some of the nuclear data. So here's the isotope bismuth-212. It'll have the mass excess, the binding energy per atomic mass, the atomic mass units, the neutron mass, the Q value for beta minus, number of different decays, electron capture, positron, neutron, proton. As you can see here, there's many different types of reactions that can occur. Decays that are calculated doesn't mean that they all will be seen, but any reaction that's positive does have a possibility, thermodynamically speaking, of occurring. And for bismuth-212, I want to note that beta minus has a positive Q value. And again, these Q values are in keV. They're not explicitly listed, but these values are in keV. And the alpha also has a positive Q value. This isotope does in fact branch. It decays about 33% by alpha and the remainder by beta minus. So if, as opposed to getting all this decay data, if one wanted to just get a specific decay, you can put in the isotope, the decay mode, and let's just say alpha, and submit. And the Q value for the bismuth-212 alpha decay to thallium-208 is shown here. And this is the Q value, and keV is listed. We could also say, well, what if we just wanted to know what would, if I have bismuth-212, what would have to decay in order to make a certain isotope? So let's say if I wanted to make lead-208. Well, bismuth-212 to make lead-208 would need a hydrogen-4 emission, very unlikely, but it will give you the Q value here. Or if I said, what if deuterium is emitted? So bismuth-212 plus deuterium yields lead-210. Now, this Q value not only can be used for, this Q value website can not only be used for the decays, but also for nuclear reactions. As we discussed in a previous slide, we're showing reactions with iron, but let's take a classic reaction. Let's take lead-208, and let's turn it into gold. And let's start off by just hitting it with a proton. And let's say I want to make 197 a gold. That's the stable isotope of gold. All right, so lead plus a proton, beryllium-12, and gold 197 could be products. The Q value is listed here. And a threshold energy, which we'll describe later in the course, is listed here. Now let's say if I did this reaction at a certain energy, what I also want to show is that this reaction, when you discuss a nuclear reaction, often many different types of reactions occur. So let's say we'll use lead-208 as a target, our proton as a projectile, and we'll use 20 MeV as the proton energy on target. And these are all the different types of reactions that can occur. And as you see, there are many types of reactions. Here's gold-201 that's made with two alphas coming out, thallium-205 with an alpha. As you can, here's just bismuth-209 emitting a gamma, so it just absorbs that proton. As you can see, for a given nuclear reaction, there's lots of different probabilities and different reaction mechanisms that can occur. These probabilities for each reaction is described by a cross-section, and we'll describe that later in the course. So you see from this Q value calculator site, you can get lots of information for a summary of an isotope, a specific decay, or any reaction you can possibly think of. The site from Russia is similar. It has a database. You can discuss decays. So we can start with our bismuth decay. Bismuth 212. Let's just make it go to an alpha particle. Thallium 208, and we get the Q value. We can do a reaction. Lead 206 plus deuterium. Let's make gold. And beryllium 11, and here's the Q value. This site we could do 3 fragments or 4 fragments. We can also do a fusion reaction. So both these sites can be used during the course. The means of doing the calculations were previously discussed, but for any time a question is related to Q values, please feel free to use this material, either of these sites, during the course. So let's review what we've gone over about Q value calculations. So Q value for the beta decay of sodium-24, sodium-24 decaying into magnesium-24, beta particle, antineutrino, Q value. Set up. Let's solve for the Q value. Remember, for beta minus decay, we can combine the progeny and the electron together, so we don't need to break out the electron mass separately for the Q value calculation for beta decay. So the Q value is just sodium-24 minus manganese-24. We get this from the atomic mass units, 931.5 MeV per atomic mass unit. This is our Q value. If we go from the mass excess values, we can pull up the information from here. We can calculate the mass excess. We get pretty good agreement. Electron capture of sodium-22. Sodium-22 is capturing its own electron, so let's make it all one atom. Neon-22, neutrino, Q value. Again, from the mass values, we get the difference in the AMU, 931.5 MeV per AMU. From the mass excesses, we can pull the mass excesses out of here. So sodium-22 and neon-22. The difference in the mass excesses is 2.843 MeV, and as you can see, it is in very good agreement with the Q value calculated directly from the masses of sodium-22 and neon-22. There's a term we've already introduced, binding energy, that comes from these energetic terms. Binding energy is the difference between the constituent nucleons and the mass of the nucleus. So if I think of a nucleus, it has so many neutrons, so many protons. I can determine the mass of that nucleus. I know the mass of neutrons and protons, and I can compare the two. And fundamentally, there's a difference in those masses, and that can be thought of in terms of energy released if all the nucleons were used to form the nucleus. The nuclear mass is not equal to the sum of the constituent nucleons. So we can talk about an energy that goes from the number of protons and the number of neutrons in a nucleus minus the mass of the nucleus. That mass must have gone somewhere, goes into the energy that keeps the nucleus together. So we'll call it binding energy. And we actually describe binding energy per nucleon, because if I have a larger nucleus, if I have more of these nucleons interacting, the binding energy will be greater just because there's more nucleons. So we actually want this average binding energy. So we can calculate a total binding energy equal to the mass of the protons plus the mass of the neutrons minus the mass of the nucleus, and then multiply it by c squared to get energy. And then I divide that by the total number of nucleons in the nucleus, and I get an average binding energy, or a binding energy per nucleon. So it describes how some of this mass is converted into energy that keeps the nucleus stable. So one of the trends that's observed is that the binding energy of an even A nucleus is generally higher than the adjacent odd A nuclei. And if we think about this, even nuclei dominate, and they tend to have the most stable configurations. Another trend that's borne out from this binding energy curve, as we see here, is that I can fuse atoms together and create energy. This is where the concept of fusion comes from, and it's effectively used in stellar processes. So stars run off of fusion. We know that we could take lighter atoms, create helium. Helium is shown right at that peak right there. But what this curve shows is that you can actually get energy by fusing elements all the way up to iron. This is in fact what stars do. One of the other things that this binding energy curve shows is fission. I can take heavy elements, split them in two, and they create elements with larger binding energies. This is a driving force for nuclear fission. We also see that energy released from fission creates these lighter isotopes. There's this maximum stability around iron. This stability is actually responsible for the observed abnormally high abundances of the iron groups in the elements right around iron. And elements up to iron can be formed in stellar fusion. So you get stars gaining energy by fusing these elements together. And we will talk about the stellar processes for making elements later in this course. So these relatively straightforward calculations can actually be used to help explain phenomena that we observe in nuclear reactions. So for example, uranium-235 can fission, can split in two, can create energy when a thermal neutron, a very, very low energy neutron, interacts with it. But uranium-238 doesn't. Let's explore, just from the energetics, what may drive this. So we have a general reaction. We've got some isotope. It absorbs a neutron. It makes the same element, one isotope up, plus energy. So let's look at the reaction of a neutron with uranium-235 and uranium-238. Calculate the Q value. So the Q value for uranium-235 would be uranium-235 plus a neutron going to uranium-236. And for uranium-238 would be uranium-238 plus a neutron going to uranium-239. We can determine the mass excess values here. Here's the neutron. Here's uranium-235, uranium-236, uranium-238, uranium-239. We get that the Q value for the uranium-238 reaction is about 4.8 MeV, and the Q value for uranium-235 is about 6.5 MeV. It turns out that fission requires somewhere between 5 and 6 MeV to overcome this fission barrier. Does uranium-233 fission from a thermal neutron? We can run that calculation. Yes, it does. And this property is actually due to the fact that when that neutron comes in, you get neutron pairing that helps drive the energetics. So we were able to describe this interesting nuclear phenomena where we get fission of uranium-235 by thermal neutrons, but not uranium-238, based on these energetic equations. Based on everything we've discussed, masses, how those masses can be used to evaluate binding energy, we can now use this information to actually develop a simple model of the nucleus. So we're going to talk about a model of the nucleus, and this model is basically going to be based on a liquid drop. Very simple. We're going to call it the liquid drop model of the nucleus. That's what it's called. And some of the concepts of this model are described here. So that the volume of nuclei are basically based on the number of nucleons present. You can't compress nuclear matter, so the size is fundamentally based on the number of nucleons. And this is the basis of the equation of the nuclear radius. Radius is just proportional to the number of nucleons. And something being incompressible, sounds like water. And the total binding energy of nuclei are nearly proportional to the number of nucleons present, so there's a saturation character. That means that the nucleons tend to only interact with a small number of other nucleons. So if we thought of water, water only tends to interact with other water around it. So it seems to be a reasonable model. Nucleons that are saturated, that have other nucleons around it, will have a different characteristic than those on the surface, because the surface nucleons don't have other nucleons around it at the surface. So we'll need to consider that term. All these together is the basis of the liquid drop model. It considers the number of protons and neutrons in a nucleus, how they may arrange, interact, and if we're also going to talk about a nuclear drop model, the liquid drop model of the nucleus, we tend to think spherical. And this is all developed from mass data, and you can get some information from this web link here. And fundamentally, what this describes is that nucleons are going to have different interactions if they're in the volume, right? If they're in the middle of this drop, they're saturated. If they're on the surface, well, they're not completely saturated. They've got some interactions here, but nothing out over here. There's a Coulombic interaction. The reds are protons, the whites are neutrons. So there's a force interaction, which is going to tend to spread the protons out. There's an asymmetry interaction. The neutrons, protons want to pair up fundamentally. And then if there's something left over, that's an asymmetric term. And then there's pairing of the nucleons themselves. So neutron, neutron, proton, proton pairs. So there's a few different terms that try to expand this model beyond just a simple liquid drop. Another way of evaluating trends within nuclei is to look at something called mass parabolas. It's a way of demonstrating stability by constructing some binding energies. So what we have here is basically a way of showing how much extra energy an isotope has compared to the other isotopes in its isobar. So here we plot A of 157, A of 75, and fundamentally here we have energies. These are your Q values. So zinc 75 decaying to gallium 75 has this much energy, gallium to germanium, germanium to arsenic, and we see that there's a stability point here at arsenic. Krypton decays to bromine, bromine to selenium, and then the selenium to arsenic. If we go to the 157, we're looking at the lanthanides, we see a similar trends. So what this shows is it's a way of plotting the energy from one isotope to another, and it also clearly identifies those stable isotopes. Those are at the bottom of the mass parabola. And for odd A isotopes, there's only one beta stable. And for even A isotopes, sometimes there will be multiple beta stable isotopes. Previous slides show an example of the A157. Here's an example of the A156 mass parabola. This is taken from the table of the isotopes. What we want to show here is that there are two stable nuclei within this trend. And again, we see this mass parabola is going to give a lot more information. We see the beta decay here. So neodymium, promethium, samarium, europium, gadolinium. We're going up in Z, and then here we're going down in Z from tantalum all the way to gadolinium. But what we see is that as we go from the beta decay side, we're going to reach a point where this europium decays to the gadolinium stable, and then on this beta positive side, we go down and we hit a point where the holmium would decay to dysprosium. Now dysprosium is at lower energy, so this is a plot, you can think of this as a plot of N for a given Z versus energy. Dysprosium here is lower than the holmium and the terbium. Now, the dysprosium is higher than the gadolinium, so there is a possibility that the dysprosium could decay to the gadolinium. Some isotopes do that through double beta decay, but the dysprosium isn't going to decay to the terbium because that's energetically not allowed, but the terbium here could still electron capture to gadolinium. So for an A of 156, we'd expect to see two stable isotopes, the dysprosium and the gadolinium. And the other thing you should note with this, for a mass parabola with two stable isotopes, you will not see the two stable isotopes right next to each other in N. So you wouldn't have stable terbium and stable gadolinium. They'd both have to be at the exact same energy level. The stable isotopes are usually off by 1 N. Right, let's further our discussion on nuclear shape. We brought this up a little bit earlier when we talked about the non-compressibility of nuclei in the liquid drop model. But there's an equation for nuclear radii that's shown here. And all it is that you're basically stating that volumes are nearly proportional to the nuclear mass because the nuclei all have about the same density. You're filling up something with more and more nuclei, it's going to expand. What it actually turns out is that nuclei are not densely packed with nucleons, that packing varies, so the density is going to vary. So we have an equation that talks about the radii, and it's pretty simple. There's a constant times a to the 1/3. So as I add more neutrons and protons, the radii is going to increase. But what it increases by, this term R naught, can vary 1.1 to 1.6 femtometers for the equation above. So that variation has to do with the areas and type of isotopes that are examined. So this variations in nuclear radii can mean a few different things, has different implications. That there's a nuclear force field, that there's distribution in charges, and that there's nuclear mass distributions. So in other words, we're trying to get some of the information that we've talked about in terms of density, in terms of masses, and use that to get an idea of the shape of the nucleus. So right now we're just looking at something very simple, the radii, and we see that there's variations. We know that it will increase the more nucleons that are added, but how it increases varies somewhat. The scattering data that was collected showed some differences in expected behavior of the nuclei, and that in turn led to the ability to describe the potentials in which the nucleus was constructed of. So in other words, the scattering experiments provided information, just like as we did with the liquid drop model. You had some models, you got some more data, you saw variations, so then you kind of change your models so that it helps explain the data that you're collecting better. So you see that it's an iterative process, which was used often. It's used in all areas of science, but the examples we're talking about today relate to nuclear properties. So the scattering experiments, the data potentially, approximately agreed with the square well potential in the nucleus. So imagine that the nucleons sit in this square well potential, the solid line that's shown here. This is for protons. You have a little bit of potential on the top here. This is for neutrons. There is no potential here. And what this means is that neutrons can easily enter the potential, where protons have to have a bit of energy to get into the potential. This has to do with charge, so it takes Coulomb's and Coulomb property into the variation. Now, the data actually seems to point to a Wood-Saxon fit. And this is the dashed lines. And the difference is you see that the square wells, it's a little bit, the distance here is a little bit smaller at the bottom of the potential, larger at the top of the potential. But the reason that you have this is that this Wood-Saxon potential can describe some of the variations in nuclear density as a function of distance from the center of the nucleus. And you can determine something about a potential by understanding the potential at the origin and applying this equation where r is the distance. R is the distance here from the center from which you get a half potential. A is a constant, and this is the potential at the center of the nucleus. So now this information was utilized. You get an R naught of 1.35 to 1.6 femtometers for a square well. This term changes a little bit for the Wood-Saxon potential if you're looking at the half potential, so where it drops from the center to the half, or this where it goes from 90 to 10% of the full potential. This R naught goes to 2.2 femtometers. And this 90 to 10% drop can be defined as the nuclear skin thickness. Here's an example of the nuclear skin thickness. Pictorial example, you can imagine it that in the center you have a very dense nucleus. As you go out towards the edge of the nucleus, the nucleon density decreases, so you get this skin. And here's an example of the density at a given distance is equal to an expanded equation where it's a function of the initial potential, the initial density. You see we have this distance here which describes this skin thickness. You can use this to start assessing different properties of nucleons, and an example, what's shown here, is what percentage of nucleons in a given nucleus are in this skin. And we see that for something that's small, like carbon-12, the bulk of the nucleons are in the skin, whereas something for heavy, like uranium-238, the majority of the nucleons are outside of the skin. So again, we're seeing some variations in some nuclear properties, and all this comes back to just utilizing information that could be easily measured, such as mass, and how it's applied. All right, we're going to complete lecture 2 by reviewing some properties that you may already be familiar with of the nucleus. And one is spin. We know that nuclei possess angular momenta that can be described through this term, where I is an integer or half integral number. That's where your nuclear spin comes in. You've used this in NMR. We want things with spin 1/2. Electrons generally distinguish between electron spin and orbital angular momentum. So again, what you may have learned about electron spin has correlations with neutron and proton spin. Like electrons and neutrons and protons have spin of 1/2, so it's a fundamental property. The nucleons in the nucleus contribute to the orbital angular momentum and the nuclear spins in a nucleus. So basically, what we're going to learn when we talk about the shell model is that the spin of a nucleus is determined by the unpaired nucleons. So if I have an even number of protons and an even number of neutrons, there's no spin. That's why on the chart of the nuclides, anything that's an even doesn't have that spin information because it's assumed to be 0 plus. Protons and neutrons we're going to see that they're going to fill shells in the shell model, just like electrons. They're going to have orbital angular momentum, just like electrons, except, we're going to go to G, H's, and I's. So they're going to be a little bit different than electrons. And we're going to see some trends. Even A nuclei tend to have 0 or integral spins, and the odd A nucleus tends to have a half integral spin. For an odd A nucleus, that the unpaired nucleon, either a proton or a neutron, is going to be responsible for the spin of the entire nucleus. All even nuclei are 0 in the ground state, 0 spin. Nuclei with non-zero angular momenta also have magnetic moments, and these are from the spins of the protons and the neutrons. From nuclear magnetic resonance, you're familiar with the terms of the magneton, so it's basically the strength of this magnetic moment. These measured magnetic moments tend to differ from calculated values, and again, that indicates that protons and neutrons are not simple structures. So again, we're seeing this trend. You do a calculation, you measure something, they don't agree, come up with a reason that they don't agree. Another term that you likely have seen elsewhere is parity. We talk about a nucleus with a given spin and parity. It's really discussing a system and if there's a sign change in the space coordinates of that system. If I take a system, describe it as a wave, perform a parity operation on that wave. If the wave functions the same, it's even parity. If the sign of that wave function changes, then it's odd parity. You can think of parity as another term to describe the behavior in quantum mechanical state of the system that you're exploring. Parity has to be conserved, so there are certain trends where even and odd parity go to odd, even and even are even, odd and odd go to even. And what this really means is if I talk about states, and we'll discuss this, as a nucleus decays and goes from one state to another, spin is important and parity is important. So as it slides into a spin state, does that spin state have a similar parity or not to the state that it's coming from? We will see that more favorable transitions occur between low spin changes and no parity changes. Parity is also connected with your angular momentum quantum number. States with an even angular momentum have even parity, so S, D states, where states with an odd angular momentum have an odd parity. P states, for instance, are odd numbers. They will have odd parities. We'll utilize this when we discuss the shell model. And what we'll see in the shell model is that the orbital in which the nucleon resides is responsible for its parity, and it'll define its spin also. So for instance, we'll see that an unpaired nucleon can occupy the F 5/2 orbital. The spin would be 5/2. F is 3, it's an odd number, so the parity is odd. D 5/2 can also be occupied. D would give it a spin of 5/2, but D being an even number, as shown here, would give the parity an even orientation. So that orbital would be 5/2 plus. And as a review, here are some properties of elementary particles: charges, rest mass, spins, magnetic moments, and if it behaves in what sort of statistics they follow. And we've talked about electron, photon, positron, neutron, and then proton within this lecture. In the lecture on nuclear properties, we explored the use of nuclear data tools and provided examples on how they can be utilized. We discussed nucleon number, particularly the number of protons and neutrons in a nucleus, and how that relates to nuclear stability. We explored the role of nuclear mass in reactions, and we talked about the mass defect to determine energetics. We also explored binding energies, the mass parabola, and an introductory nuclear model based upon a liquid drop. This lesson also explored how to determine Q values in a number of different routes, including calculations, finding the data for specific reactions, or calculating specific reactions from the Q value calculator. We discussed how nuclear radii are determined. We talked about nuclear potentials and models, and also briefly discussed nucleon distribution within the nucleus, how nuclear matter density changes as one travels from the center to the edge of a nucleus. We also explored some quantum mechanical terms, and this is fundamentally a review, terms you should have seen previously. Here's an example of some questions you should be able to answer after this lecture. What is binding energy? Well, it's just the difference between the constituents that make up the isotope and the mass of the isotope itself. The total binding energy is shown here, where I take the number of protons, that mass, add it to the mass of the number of neutrons, and subtract the actual mass of that isotope. The binding energy is positive, and this binding energy can represent the change of that mass that goes into some energy that keeps the nucleus together. What does this binding energy predict? Well, it predicts a few things. One, that if I look at binding energy as a function of mass number, we get this binding energy curve. We see that there's some properties to this curve. As I go up to about from A of 1 to 56, I keep increasing. So this means if I take elements and put them together, I can fuse elements and gain energy. When I get to this iron group, this peak iron group here, I have a maximum value, and this is one of the reasons that iron has a relatively high abundance compared to other elements. So the iron group, that elemental abundance is related to this nuclear property. And then finally, I can fission an isotope, something that's heavier. I can go from something heavy to something lighter. The binding energy increases, so energy gets released. Now the question could be relationship between stable isotopes and the number of neutrons and protons. Well, we discussed that of the stable isotopes, over half of them are even. About an equal number are even-odd, odd-even. And there are only 4 stable isotopes with odd number of neutrons and odd number of protons. So even nuclei tend to be the most stable. Some other questions you should be able to answer at the end of this lecture are shown here. What is the Q value? Well, the Q value is the energy, and it's based upon the difference between the parent and the progeny for decay, or their reactants and the products for a nuclear reaction. How can one find the Q value for decay or a reaction? Well, you can use the mass excess. You can go to the mass excess database, get the mass excess for all the components of your decay or your reaction, set it up in an equation, reactants minus products, just as you would in a chemistry reaction, and then determine the Q value. You can use the Q value calculator from the website. You can get the table of the isotopes and get the data if it's from a decay, or you can go to the chart of the nuclides on the web and also get the same decays. The difference for the chart of the nuclides is that you can get Q values for reactions that don't occur. And as a note, those Q values for decays that are positive are likely to occur or can be thermodynamically possible to occur, while those Q values that are negative are unlikely or thermodynamically unfavored to occur. How can you calculate the nuclear radius? Well, through this simple equation that's based upon the total number of nucleons. R equals R naught A to the 1/3. R naught varies from 1.1 to 1.6 femtometers. And generally speaking, 1.2 is a good number if you don't have one, if you don't know what value to use. 1.2 fits the broadest number of nuclei. And what are some properties of the nucleus that can be measured? These are some of the fundamental properties: nuclear spin, the parity, and the magnetic moment. Magnetic moment is obviously a term that if you do NMR spectroscopy, you utilize this magnetic moment term. When you have completed Lecture 2, please comment in the discussion section and respond to the Lecture 2 quiz. This lecture went over some of the tools that are available from the National Nuclear Data Center site at Brookhaven. These included the nuclear wallet card, the Q-value calculator, and also the IAEA isotope browser, which is not from Brookhaven, but rather from the International Atomic Energy Agency. Some important concepts that were covered in this lecture include the number of neutrons and protons in a nucleus can influence the stability of that nucleus, that the nuclear mass is used for identifying trends, and we can understand this from doing Q-value calculations. And one of the areas that we explored was binding energy and how trends in binding energy provide information on whether nuclei can undergo fusion, fission, and we discussed this in terms of the stability of the iron elements. We talked about binding energy and nuclear reactions. And we also reviewed how nuclear radii can be determined from the number of nucleons from a very simple equation. And we also discussed that nuclei have a skin where the thickness drops from 90% to 10%. We also talked about some terms, particularly spin and parity, And we will see that spin and parity is important when we discuss decays. We'll introduce this in the lectures on alpha, beta, and gamma decay.